Okay, so we're gonna continue with numeric. Oh, I should press record. Yeah, I know. I think I threw myself off by not doing the music. I shared the screen, but apparently because it wasn't coming from Spotify, you didn't actually hear any of the sound, which I apologize for. Okay, so we're gonna continue with numerical integration, and then we're gonna move on to a new topic. So let's do this. Let's go into writing mode. Okay, that's not working. That's not working. There we go. Oh, I should spotlight myself. Spotlight. There we go. Okay, and where did the screen go? Oh, there it is. Okay, so we've been talking about numerical integration, like what do you do if you don't have an antiderivative? We talked about the trapezoid rule. And we talked about that there is a way to estimate the worst case scenario for how wrong your Riemann sum or trapezoidal estimation might be. Yes, there, I said it right. Okay, so if you look at the screen here, you can see that we did this example with like the square root, right? And the question was like, oh, let's see how accurate it is. What's the actual answer for the area under the square root? What is the estimation that the Riemann sum would give you, and then what's the estimation that the trapezoid rule would give you? So we found out that the actual area under this curve was, oh, right here we calculated it 2/3, and when we calculated the Riemann sum, we got 0.76. And then when we calculated the trapezoid rule, we got 0.64. So it ended up being that the relative error of the trapezoid rule is 3.5%, but the relative error of the Riemann sum was 13%. Okay, so we talked about how you need to compare the relative errors to get a good idea of which one is more accurate, because you need to compare it to the thing that you're estimating. And then we talked about there's this formula here to find the accuracy of the midpoint of the Riemann sum and the accuracy of the trapezoid rule. Okay, so now we're going to talk about another method for estimation. It's called Simpson's rule. Okay, so what is Simpson's rule? Just opening it up so I have it here. So I'm going to draw a picture of what inspires this. So let's put in a nice XY axis. Let's draw the function. And let's say that we're estimating from x equals a over to x equals b. Okay, and we're going to copy this because it's nice to have the several different copies. Okay, and then we're going to paste one right here, and then we're going to paste another one right here. Okay, that way we can compare them. Okay, so, oops, there we go. Okay, so one of the ways to estimate this is with the rectangles. So let's just draw in some rectangles. Boom. 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 We've got 1, 2, 3, 4, 5 rectangles. So we're going with n equals 5. Okay, now there's a problem with this because, like, it underestimates, it overestimates, it overestimates, it overestimates, it overestimates. Okay, so you can see you have a problem here. And we found out that there's a way to estimate how wrong it will be. So because the tops of the rectangles don't follow the function very well, the cool idea, so this was just the Riemann sum. Oops, okay, I can't write today. I think it's only one n. This is the Riemann sum. It uses rectangles. The rectangles go under and over sometimes, which we don't like. So what was the brilliant idea? Like, well, we had it split into 5 parts. 1, 2, 3, 4, 5. 5. 1, 2, 3, 4. 6. That's too far. 1, 2, 3, 4. Okay, so the brilliant idea was, instead of using rectangles, why not use trapezoids? Okay, and the cool thing about using the trapezoids is that they follow the function sort of well, right? Like, let's draw some of them. So there's a line. There's a line. There's a line. There's a line. Okay, so if you draw the trapezoids, they'll go something like this. Okay, so these trapezoids follow, here, let's put trapezoid rule. The trapezoids follow the function as it goes up and down, right? So if you look at this first trapezoid right here, you can see that it goes up with it, and then in the second trapezoid, it goes down with it, right? So that because it follows the function, you don't have this problem that the rectangles have where it goes over and it goes under as much. So if you go to the next one, you're like, oh, that follows it pretty well. If you go to that one, you're like, it follows it pretty well. It's only when you have this dip right here that the trapezoid doesn't follow it very well, and you get that it goes over it. Right, so the function, if we were to sort of like zoom in, the function has that dip right there, and it just so happens that the trapezoid goes from here to here. That's where the top of the trapezoid is, and you have an overestimation. Does everyone see what I'm drawing right there? How you have like the function in blue? Oh yeah, you guys are probably like writing because you can copy it like me. All right, so there's your f of x, and then here's the top of the trapezoid. Okay, so like in the cases where the function was just like, say, going down like so, like in that case, and the top of the trapezoid follows it decently, it provides a good estimate. So this one is good. This one over here is bad. Okay, so looking at this, it's good when the function is just going down or when the function is just going up because it can follow it. When does it not end up working? Like what is the function doing so that the trapezoid provides some sort of over or underestimate? Right, it goes up and it goes down, right? It's not just monotonically increasing or decreasing. So someone had a brilliant idea about how to fix this. They said, oh, I know. Why don't we, instead of using trapezoids or rectangles, what we're going to do is we're going to use parabolas. So 1, 2, 3, 4. Okay, so if this is where, let's draw the lines. Okay, so what you do is you say, okay, I'm going to choose these 2 points, and let's draw a parabola through it. And I'm going to choose these 2 points, and I'm going to draw a parabola through it. I'm going to choose these 2 points, and I'm going to draw a parabola through it. I'm going to choose these 2 points, and I'm going to draw a parabola through it. I choose these 2 points, and I'm going to draw a parabola through it. So because you allow yourself to curve, you know how a parabola, like if you have 3 points, you can fit a parabola through it like this. So everyone see I have 1, 2, 3 points. Any 3 points can fit, a parabola can fit in them. So what you do is you take points on your graph and you fit them, and the tops are going to be parts of a parabola. And because the parabola can follow the curve of the function, it can swing up and down with it over different segments. So this is what Simpson's rule is. The tops are not just straight lines to make trapezoids. The tops are going to be parabolas. So you have your bottom right here, you have a thing right here, you have a thing right here. And then the top, you take this point, you take that point, you take like the point right before, and then it fits it with a parabola. And that's the area that you want. 1 second. All right, there we go. Okay, so you're going to get this parabolic top, which will allow it, which is what allows it to follow the curve of the function. Okay, so let me just give you the rule for Simpson's rule. This is how the estimate for Simpson's rule works. We won't go over the derivation. Okay, so it's very similar to the other ones. So you're going to take your delta x, you're going to divide by 3, and then you're going to multiply by f of x0 plus let's color code this. 4f of x1 plus 2f of x2 plus 4 of f of x3 plus 2 of f of x4 plus f of x5 as an example. Okay, so it looks sort of like the trapezoid rule. It looks like the trapezoid rule in the sense that the first two terms, you just plug in the values. Now what changes is the stuff in the middle. If you look at these two terms, you see how they're odd? The odd terms, you're going to multiply by 4. And then the even terms, you'll multiply them by 2. Okay, so Simpson's rule only works when n is odd. Yeah, oh no, does it work only when n is odd? No, never mind. That's not true. I don't know why I was thinking that. Okay, and Simpson's rule also has an error estimate. Okay, so the error estimate at worst is going to be m times b minus a over 5 divided by 180n to the 4th, where a and b are the endpoints of where you're integrating between. N is the number of segments that you're breaking it up into, and then m is equal to the maximum of the second derivative on the interval that you're estimating. Okay, so we'll do an example. Okay. So example, ooh, I know, let's make this one interesting. So let's draw it first. Okay, so let's say your function is going to look like this. Let's say this right here is 0, -2, and 4. So our function is going to be f of x is x plus 2 times x plus 4, which if you multiply that out, is going to be expand x plus 2 x minus 4. If you multiply that out, you get, sorry, switching between them is hard sometimes, x cubed minus 2x squared minus 8x. Okay, and I want to estimate the area between 0 and 4. So we are going to estimate the integral from 0 to 4 of f of x. And let's do this with n equals 4. Yeah. Actually, no, let's do it with fewer. Let's do it with n equals 2. Okay. So we'll do it, we'll break it up into 2 parts. Now, you can imagine if you were doing this with, what's it called? Like the midpoint rule, you would get a rectangle like so, and you would get a rectangle like so. So hopefully it would balance out. Sort of hard to say what would happen. And if you were doing it with the trapezoid rule, you would get a thing like this, and you would get a thing like this. Like that would be fairly accurate. So let's just first start by estimating what the error is going to be. So let's estimate what is the worst case scenario for the error. Okay, now you have to remember it's m times b minus a to the 5th over 180 n to the 4th. We'll deal with m in a moment, but your b is 4, your a is 0, and our n is 2. So, what the hell is 4 to the 5th? 4 to the power of 5 is 1024. So we get 1024 m. And then you get 4 times 180, 360 times 2, that's 720. Okay, and then what does 1024 over 720 become? Apparently 64 over 45. So you get 64m over 45. Okay, now we need to calculate the maximum value of m over our interval. So let's take the second derivative. Question, someone messaged me. Isn't the 2 to the 4 in the denominator part? Oh, shoot. Yeah, I put 2 squared. This is supposed to be 2 to the 4th. Thank you for catching that. Okay, what's 2 to the 4th? 2, 4, 8, 16? Okay, so we need 16 times 180. Shit. Okay, so that's a different number. That's 2,880. Okay, so that changes that number substantially. (16 over 45). So you get 16m over 45. Thank you for catching that. Okay, so now we need to figure out what m is. How are we going to figure that out? We need to calculate our derivative. First derivative is 3x squared minus 4x minus 8. Second derivative will be 6x minus 4. Okay, 6x minus 4, we know looks something like this. Okay, now if you're only caring about what happens between 0 and 4, your maximum will occur at 4. So we know that m will be whatever the second derivative is at 4, which will be 24 minus 4, which is 20. Oh, I hear someone's music. Who is that? Oh, they killed it. It was soothing for a moment. Okay, back to this. So your m is 20. Okay, so now we can plug it in. Our estimate at worst will be 16 times 20 over 45. Why plug in 4? Oh, because you need to find the maximum value for the second derivative. The second derivative is 6x minus 4. That's an increasing function. So that means its maximum will occur at the greatest value. So you want the biggest value between 0 and 4. Looking at 6x minus 4, we know that its greatest value occurs at 4. Does that answer that question? Person who asked me. Someone was asking, like, why plug in 4 into the second derivative? It's because it's monotonically increasing, it attains its greatest value at 4, which ends up being 20. Okay, so now we plug that in and we get, hey, what is 20 times 16 over 45? And that ends up being 64 over 9, which as a decimal, 7.11. So how big can our error be at worst? 7.11. Okay, we'll find out what the actual error is in a little bit. Okay, but are there any questions about the calculation in terms of the estimation of the error? Okay, so now we're going to estimate using Simpson's rule. So n is going to be equal to 2, which means our delta x is going to be b minus a over n. Our b is 4, our a is 0, our n is 2. So we get each thing is 2 wide. Okay, x0 is our a, which is our starting point, which is 0. Then our x1 will be that plus delta x, which will be 2. And then our x2 will be 4. So remember, the way the formula works is that it's delta x over 3 times first term is always itself, and then odd terms are going to be multiplied by 4, and then it ends at this one. The last one is just itself. Okay, so now we need to plug in those numbers. So we're going to get, our delta x was 2, so you're going to get 2/3, and then we want f of 0 plus 4 times f of 2 plus f of 4. Okay, so I'm going to go and I'm going to calculate that in Wolfram. So our f of x was x cubed minus 2x squared minus 8x. So I want 2/3 times f of 0 plus 4 times f of 2 plus f of 4. And when I plug that in, I got -32. So, oh, I see why it doesn't make sense. My function actually looks like this. I see why. 1 second. My function looks like this. Because it's a cubic. We're estimating the area between 0 and 4. It's actually, that's the area you want, which is why it makes sense that it's negative. Okay, so my estimated area, using Simpson's rule, is negative 32. We said that the worst case scenario is that it would be off by 7.11. I'm going to go and I'm going to have Wolfram give us the actual, I'm going to have Wolfram integrate it for us. So I'm going to have it integrate between 0 and 4. Well, that's not good. I had Wolfram integrate it for us, and it says that if you integrate from 0 to 4 our f of x, that the area is approximately equal to negative 42. Why am I sad? There's something wrong here. It's telling me that the area is about equal to negative 42.666. Why am I super sad? Yeah, because it's more than what the air supposedly is. Is there a 2f of 2? No, because I'm using n equals 2, which means there's only 3 terms. Because terms with odd indices, like x1, have to have just a 4. And then this is the final term, so it's just by itself. The air shouldn't be that big. That's not good. Oh my, this is one of those days. I must have screwed up somewhere. Oh yeah, not 2f of x2, because it's the last term, it just is by itself. But I see what you're saying, Anshul. We won't worry about this. I showed you how to use it. I'm not sure why they're not in agreement. That is really odd, though. The actual integral is about negative 42.66, but my estimated area is negative 32. And supposedly, the worst case scenario was 7.11. Maybe I calculated that wrong. Let me go back and redo that. So it would be 4 to the 5th times m, which is 20, divided by 180 times 2 to the 4th. Oh, no, 7.11. The worst case scenario for the air is supposedly 7.11. But we're getting an error of about 10, 9 and 2/3. Actually more, 10 and 2/3. That is really weird. Yeah, maybe I did. Oh no, I tried it. Let me look. Yeah, maybe I did plug it in wrong. Oh, you're having the same exact problem. Or it's like, wait a second, why is this not working? Okay, let's make sure I just entered the function right. X cubed minus 2x squared minus 8x. Okay, cool. I did that right. I had to integrate from 0 to 4. I got negative 42. For my estimate, I put 2/3 times f of 0. Oh, plus, I did enter something in wrong into Wolfram. Oh, okay. When I entered it into Wolfram, I accidentally put a 3 here. So I fixed that. Okay, the actual estimated area. Okay, thank God. This is... Oh. Okay, guess what the actual estimated area is? Negative 42.667. Okay, there we go. It's basically perfect. Yay! Oh my god. I was like really worried. I was like, did I break something? My bad. I did type it into Wolfram wrong. It basically only differs in the third decimal place. So the error was like 0.001. Oh, thank God. I was like actually getting really worried there. I was like, what did I do? Okay, so I entered it wrong. My bad. So I guess what I want to show you is that Simpson's rule. It actually is like super accurate for a lot of things because it has those parabolic tops. Okay, there we go. Boom. Woo! Yay! Okay, we're done with numerical integration. Okay. To be honest, so Matthew was saying, like, why not just use, like, we should just use this instead of antiderivatives. Did you know that's what the basis of numerical computing is? Like, when physicists, like, run simulations and stuff, they actually never do symbolic integration. The computers just do stuff like this. And actually, let me quickly show you. There's a Wikipedia article about this. Let me go to share my screen. To be honest, like numerical integration works really well. So if you can see that they have, so in numerical integration, like one of the things they talk about here is like the different types. So you have like the generalized midpoint rule, and then you have these adaptive algorithms. So the ones, let's see if we can find it. So there's trapezoidal rule. The one that's like used most often is this one, I think. So they have like a whole article about the trapezoid rule, but the one they use is it's a lot like Simpson's rule basically, and it uses quadratics, and it's super accurate. It says implementations that is implemented by something called QuadPack. So QuadPack is like a very common. It's like basically programmers have written programs so that you give it a function and you tell it, hey, I want you to integrate this for me, but I want you to do it numerically. And like these are like super famous. They use a programming language called Fortran, which like is physicists use to run a lot of these calculations. Like to be honest, like no one really does symbolic integration anymore. It's all done by computers using like things very similar to Simpson's rule. Okay. Let's move on now. Okay, new page. So we're going to do something called improper integrals now. Rename. Improper integrals. Zoom in to 300%. There we go. Okay, so up till now, when we've been doing definite integrals, we've been finding the area between a and b under f of x. So let's like draw the picture. Okay, so here's your f of x. And here is your a. And here's your b. And the area here that I've highlighted in red, that's the answer to that definite integral, right? Okay, so it's called a definite integral because you have a definite region over which you are accumulating area, right? You are accumulating area between A and B. Okay, now the question is, well, what if you want to do something sort of crazy? Like, you want to start at A, and then you just want to accumulate area forever. All the way off until infinity. How do we do that? So instead of going between two particular definite numbers, like A and B, you start at A and then you accumulate area all the way off to infinity. So let's like run through some examples here. Let's say that your function is something super simple, like f of x equals 1, 2, 3. 3. So you see how f of x is just the constant function 3? Now, let's say that you're starting here at a equals 1. And here's your b over here. So if you are integrating from 1 to b of this function, which is just 3, what do you know that the area of this is going to be? Like, we know that the height of this thing is 3, and then what's the width of this rectangle going to be? Yeah, b minus 1, excellent. Okay, now you can imagine that this formula works. Like if you just keep on making b bigger and bigger, you just plug in whatever your b value is, right? So if like b was 1,000, you would get 3 times 1,000 minus 1. Okay, now here is what's the problem. What happens as b approaches infinity? What happens to this area? Yeah. The definite integral approaches infinity as well. Let's just put arrow infinity, which is a no-no. We like infinite area. We don't like that idea. We would call this an example of an integral which doesn't converge. We're only going to allow ourselves to integrate over an infinitely wide area if your area goes to a particular number. It can't just get bigger and bigger forever. Does that sort of make sense? Like we're not gonna allow ourselves to say, oh, let's integrate from 0 to infinity of 3. Because what that just ends up being is equal to infinity. So we would say that this integral doesn't converge because you get an infinitely large area. Does that make sense to people what I'm saying? Like if you just keep on expanding out that rectangle, it gets infinitely large. We don't like that. Cool. Okay, so what we want is something that will go to a particular size. Yeah, so the limit of the Riemann sum. Yeah, you would want the limit of the Riemann sum to approach a particular number, not like infinitely large. So to make that happen, what you need is something like this. So let me like put in a axis. You're going to need a function that does this or something like it. So like here's the a where you're starting from, and you're integrating over to b. And then you start asking yourself, well, what about if I was just to integrate from a to infinity? Now this one might converge because as you keep on moving b over, what happens to the amount of area that you add? Here, let's extend this function out. Yeah, it keeps on getting smaller. It adds less and less and less. So like if you move b over to here, or over to here, or over to here, you notice that the area that you start adding, like the amount that you're adding keeps on getting smaller and smaller and smaller, right? So does it make sense because you keep on adding less and less area, that it might actually add up to a particular number? Okay, and the way that we're going to calculate this is we're going to imagine integrating from a to b of your function f of x dx, and then we're going to take the limit of that. So if you want to integrate from some number to infinity, you're like, okay, we'll just first integrate from a to b, and then we'll take the limit as b goes to infinity to see what happens. And you have two possibilities. Either the integral will converge, in which case you'll get a number, or it will diverge, in which case you'll get like infinity. Okay, these are called improper integrals when you have like from a to infinity. You know how we have definite integrals? So the improper integral, oh, well, okay, yeah, so sine and cosine, good question. That one's like really weird. Because what's going to happen with this part up here and that part down there? Okay, they'll cancel. But then as you extend it out a little, what's my answer if I'm stopping right here? What can I say about my answer if I was to stop right here, if that was my b? It would be positive. But what happens if I was to extend out to right here? What would my answer be? Negative, right? So because it would keep on switching back and forth, that would also diverge. So I guess really it could go to infinity, or what it does is it oscillates. Because that would be an example of a divergent integral. But just to go back to the terminology, an improper integral is when you go from a to infinity. The way you solve improper integrals is by taking the limit of a definite integral, right? You change the top number into a definite value, you calculate it, and then you see what happens is you take the limit. So let's do an example. Let's say, let's say that you want to calculate the improper integral from 0 to infinity of 1 over x. Okay, so the way you're going to do this is you're going to do the limit as b goes to infinity, integrating from 0 to b of 1 over x. Okay, now what is the antiderivative of 1 over x? What has a derivative equal to 1 over x? Do we remember? Yeah, natural log. So what you have here is the limit as b goes to infinity of, so you need f of b, so that's going to be natural log of b, minus the natural log of 0. Oh, okay, let's change this problem. Why do I not want 0 there? We need to change the problem. What's bad with taking the natural log of 0? Yeah, it doesn't exist. So let's change the bottom integral to 1. That way we can have natural log of 1. What is the natural log of 1? Yeah. No, it's 0. Because e to the 0 is 1. So that goes away. And you get the limit as b goes to infinity of just the natural log of b. Now, what happens to natural log? If you keep on plugging bigger and bigger numbers into natural log, what do you get? So if you keep on plugging bigger and bigger numbers into natural log, what does that approach? The limit of the natural log of b as b goes to infinity is what? Plug bigger and bigger numbers into this. What happens to its value? Does it go to a particular number? Yeah, it goes to infinity. Okay, what that means is, if you look at the function 1 over x, oops, okay, that's poorly drawn. And you start accumulating from 1, and you just keep on adding more and more area under that curve, do you ever stop adding area? No, it accumulates infinitely large area. Even though 1 over x gets shorter and 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 shorter. You know how it's an horizontal asymptote? 1 over x, it keeps on going down like this. If you were to start accumulating area forever that way, you never stop adding area. You don't get a particular number. So this is a divergent improper integral. There is no definite area under 1 over x between 1 and infinity. But let's do a different one. Let's do the area from 1 to infinity under 1 over x squared. So that's an improper integral, and we can turn it into the limit as b goes to infinity, integral 1 over b of x to the minus 2 dx. What is the antiderivative of 1 over x squared? So what's my antiderivative here? It's going to be minus well, it's not minus x, it's minus x to the negative 1, right? So it's minus 1 over x. That's cool, it's cool. So what do you get there? You get the limit as b goes to infinity of, so you need big F of b, that would be minus 1 over b minus 1 over 1 okay, these two minuses will cancel, so that's going to be a plus 1. So you're going to get the limit of 1 minus 1 over b. Now, as b goes to infinity, what happens to this 1 over b term? So what's the whole limit equal to? 1, which is super cool. This is telling you that if you look at that function, 1 over x squared, which looks super similar to 1 over x, looks like this, right? It also has an asymptote. If you start accumulating area from 1 right here, and you keep on accumulating forever, what's the area under all of that going to be equal to? 1. Even though it stretches on forever and ever and ever. So this one converged. Yeah, yeah, it is. Somehow, and they look so similar. If you graph 1 over x and 1 over x squared, they look basically the same. But 1 over x squared approaches its horizontal asymptote slightly faster. Like 1 over, like if you were to graph it, 1 over x would look like that the whole way through, and then 1 over x would look like this, or 1 over x squared. And then here's like the x-axis. Does that make sense? Like it's just slightly smaller, and somehow one of them has infinite area and the other has an area of 1, from 1 to infinity. It's weird. Alright, this is where we need to end. This is going to be a big thing that we're going to explore basically for the rest of the semester.